Effect of substituents on the pKa of substituted phenols, benzoic acids, and protonated anilines. The pKa values of substituted phenols, benzoic acids, and protonated anilines can change depending upon the substituent present on the ring structure. Let's say that we have an electron withdrawing group present on phenol. When this hydrogen is lost, then it's going to result in a conjugate base. But this conjugate base is stabilized because this electron withdrawing group is going to pull some of these electrons towards itself, right? So there is lesser electron density on this oxygen. And if the conjugate base is stabilized, then definitely the acid should be a strong acid, right? If we have an electron withdrawing group attached to it, if Z is going to be an electron withdrawing group. On the other hand, if the Z is going to be an electron donating group, then it's going to release some electrons towards the ring, and then those electrons can go onto this oxygen. So this oxygen is now going to have more electron density. Therefore, phenols in which we have an electron donating group present on it are said to be weak acids because this hydrogen cannot be lost easily because of the higher electron density on that oxygen. Here are some examples for substituted phenols with their pKa values. Phenol has a pKa value of 9.95. Let's take a look at the compounds on the right and on the left. The compounds on the right have deactivating substituents, whereas the compounds on the left have activating substituents. Now, when you have these activating groups right here, it's going to donate the electrons, right? As it donates the electrons, there is going to be greater electron density on oxygen, and therefore this bond right here, the OH bond, the bond between oxygen and hydrogen will be strengthened. Or in other words, when this hydrogen is lost, this oxygen will be having more electron density on it, which will destabilize the conjugate base. On the other hand, when you have deactivating substituents, the deactivating substituents are going to pull the electrons, right? As they pull the electrons, the bond between oxygen and hydrogen will be weakened, and therefore the hydrogen can be lost easily, and also the conjugate base will be stabilized because you do have an electron withdrawing group. This is the reason why we have higher pKa with electron donating substituents and lower pKa for electron withdrawing substituents. Here, this would be a weak acid, since this group right here is strongly activating, whereas the nitrophenol is a strong acid because the nitro group is strongly electron withdrawing. This is exactly for the same reason why para-nitrobenzoic acid has got a lower pKa. So here again, the nitro group is electron withdrawing, and therefore this hydrogen, when it's lost, those electrons that is left behind on this oxygen can be easily stabilized because of the presence of this electron withdrawing group. So this one is going to be a strong acid, and the one with an electron donating substituent is going to be a weaker acid. Here is one more example. We have protonated aniline. Protonated aniline has a pKa value of 4.58, but anytime it has substitution on it, its pKa value is going to change. This time we'll take an example with methyl group on the protonated aniline and with the aldehyde group on the protonated aniline. So methyl group is going to donate the electrons towards the ring through hyperconjugation, and because it's an electron donating group, let's see what's going to happen to the conjugate base. Let's write down the conjugate base that it will be obtained. So here is the conjugate base that will be obtained. But these electrons right here that is present on nitrogen, after the hydrogen has left, it's going to stay on the nitrogen. It's going to increase the electron density on nitrogen because this CH3 group is going to donate the electrons through hyperconjugation. But when we look into this compound right here, which has a moderately activating substituent, which is going to withdraw the electrons towards itself, the conjugate base will be stabilized. So let's draw the conjugate base here again. So here will be the conjugate base. And you can see that there is an electron withdrawing group substituent present, so because of which these electrons can get delocalized onto the electron withdrawing group, right? So because of this, this is going to be a strong, comparatively going to be a stronger acid. This one is here is a weak acid.